Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Farid bin Shamsukaha and my number metric is DE210095. So today we are from Group 5, Section 3. We'll present our high voltage group project, which is electric field characteristics for 132 kilovolts polymeric post insulator. So this is group members of our teams, which is first Muhammad Amin Haikal bin Khairul Anwar, Syarul Adli bin Sufi Kausni, Muhammad Farid bin Syamsukaha, and Nick Hairul Hazrel bin Nick Fazil. So for the project background is overhead line insulators provide both electrical insulation and mechanical support for conductors, prevent electricity from passing through or over its surface under normal and transient voltage, pollution noise, and others. Strong enough to withstand the weight of conductor bundles and extra loads like ice, snow, wind, and damaged wire. Typical of overhead power line insulator is first suspension insulator, which is used for suspension towers, and second tension insulator, which is used for angle or tension towers. Next is problem statement. So there are three problem statement. First, outdoor overhead lines insulator face a variety of issues that affect their efficiency and all grid stability. Second, flashovers induced by a combination of conditions such as excessive moisture, pollution, and aging insulator can result in power outage and equipment damage. Third, bird activity and animal-induced conductors vibration can stress and degrade insulator hardware, increasing the danger of flashovers and line faults. So our objective is first to design the overhead line insulator prototype. Second, to simulate and analyze the normal voltage and electric field distribution on the design prototype. 3. To work out and select the suitable standard test setup to test the proposed prototype. And fourth, to propose a standard code of practice to safety conduct the test on the prototype. So for the scope of the project is first design a high voltage 2D or 3D insulator using drawing software. Second, simulate and analyze the normal voltage and electric field distribution using FEMM software on the design prototype. Third, analyze the prototype performance under environmental stress. Fourth, provide HV testing test set that take procedure, safety, and equipment into account. So outcome of the work is first, better design for insulator. Second, performance analysis with optimization. Third, standardized method for testing. And fourth, increasing resilience to the environment.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nihairul Hazrul bin Fazil. My number metric is DE210045. So for the technical summary, the first is polymeric silicon rubber post insulator. Polymeric post insulators, also known as composite insulators, are electrical insulators used in power lines. They consist of a fiberglass core for central support and insulation, surrounded by silicon rubber, a lightweight, durable material. Silicon rubber hydrophobicity repels water, preventing leakage or flashover due to electricity conductivity. This reduces maintenance requirement and enhances power grid reliability, making it a cost-effective alternative to traditional materials like porcelain or glass. Overall, silicon rubber offers a numerous advantage over traditional materials. So this is our design of the post insulator, as you can see for the for the left side. So for the properties of the post insulator, the system voltage is 132 kilovolt, types long rod. Material we use is polymeric. The length is 1540 mm. The clippage distance is 5200 mm. The conductors are 175 mm square AAC, and the fitting is bolts and nut. This is the block diagram for the process flow FEA simulation. The first part is problem formulation. Define geometry, material characteristic, and boundary condition. For the pre-processing, create or import the geometric model into FMM. For the solver setup, configure solver parameters for different conditions. Example, dry, wet, salty, pollute. Simulation execution, use the FEMM solver to perform the simulation. And the last one is post-processing. Extract and visualize quantifiable data. And this is the flowchart for the feed simulation. The first one is we start and define the problem for the insulator design. Next, design the 2D modeling for the silicon rubber insulator. Set the properties for the 2D modeling such as the boundary, material, and conductor. Next, we use the solver setup. Set the test condition for the modeling. Simulation execution, run simulation and monitoring, post-processing, result visualization, data extraction, analyze, and evaluate the voltage distribution and electric field, and it's end there. This is the methodology, which include electrical requirements, mechanical strength, material selection, insulator design, bolt and nut design, simulation and analysis, prototyping and testing, and validation and optimization.
Hello and Assalamualaikum. Okay, for the FEA simulation result, as we can see, the middle picture is the photo for the 132 kilovolt post insulator using silicon rubber. And for this design, we have two sizing of singly that is 143 mm, and the second one is 113 millimeter. Okay, based on this simulation, the FEM simulation relief on the environmental parameter for its analysis. The FEM finite element method outcome is contingent upon the following condition. The first one is dry with the clean air. Second one dry with contaminated air. Third one wet with clean air, and lastly wet with contaminated air. Okay, as we can see for this slide, that is for the simulation during the dry with clean air condition. Okay, for the property, for the silicon rubber that is that is 12, Ez is 12, and charge density is 0. For the value of the property for the metal value that is ER1 and EZ1. As we can see when we run the simulation, the voltage distribution and the field intensity result is shown based on the figure. Okay, for this slide, that is the simulation during the wet with clean air condition. For the wet, we put at the uh, corner of the single disc. So for the wet, ER the value property that is 10, EZ is 10, and charge density is 1 with the power of negative 9. So the result is shown in the figure. That is for the voltage distribution and field intensity. So for the next simulation, that is the contaminated air condition. As we can see, these are the result for for the simulation for the voltage distribution and field intensity for the dry with contaminated air conditions. Okay, for this one, the simulation is for the wet with contaminated air condition. So this is the last simulation for our case study for the different type of weather condition. So the figure show the voltage distribution and graph for voltage, and the right one is field intensity, and the graph show for the field intensity.
Assalamualaikum warahmatullahi wabarakatuh. My name is Syarul Adli bin Zulkifli Husni. My number is DE21016. So I'll continue with the analysis of FA simulation result. So the insulator failure can caused by the environmental instability, high electric field, mechanical strength, and ambient factor. So a polymeric post-insulator design for a 132 kilovolt system voltage is proposed, consisting of 9 discs connected to a core at a creepage distance of 5,200. So the FEMM software was used to simulate a contaminated environment with 4 different scenarios. So the modeling program enable monitoring and quantifying voltage distribution and electric field generator on the insulator. Okay, next is the FEA simulation result. So this is the comparison between dry and wet with clean air. Figure 5.12 and 5.13 show that the insulator's top part has a high voltage distribution than the ground region. So the area's high voltage distribution is represented by pink, while the system ground is represented by light blue. So the voltage in each condition is identical but has disturbance, making it unaffected by moisture or dryness. The voltage remains unchanged in dry with clean air condition. So next is the figure 5.14 and 5.13. It shows that a dry and clean environment generates a higher electric field than the wet and clean environment. So the intensity starts at 3.2 E5 V per M, with the insulator length varying from 60 to 190. The clean the wet clean condition has a lower value than the dry condition, with a peak value around 3 e power of 5 V per M towards the end. So the wet with clean condition has a smaller value at the start and a greater value at the end. So the water on the insulator surface can affect the wet with clean state pattern. Okay, next is the comparison between dry and wet with contaminated air. So our insulator design was test for pollution flashover characteristic under simulated contamination scenarios, focusing on salt, a common pollutant in transmission and distribution line. The simulation findings showed consistent voltage distribution across study situation, with a decline curve divided into three sections based on structure height. The potential difference reduced faster at ends, with the side string showing more downward trend. Comparing electric field strength of two insulators under dry and wet condition with salt as a contaminated agent, the dry condition with contaminated air has significant higher strength at both ends. Contamination on insulators alter salt condition pattern, with airborne sea salt particles being primary source. Sea wave release water bubble due to harsh weather, increasing electric field strength on the insulator surface through salt deposits. Okay, lastly is the conclusion. The project involved designing and testing a high voltage insulator. The design was based on a provided prototype and created using AutoCAD software for both 2D and 3D views. To analyze the insulator performance, FEMM software was used to simulate its behavior under four conditions, which is wet or clean air, dry or clean air, wet contaminated, and dry and contaminated. So the result shows that voltage remained relatively stable across all conditions, with some minor disruption in wet scenario. However, the electric field strength varied under all conditions. To This variation were deemed acceptable for the insulator operation. Notably, the wet condition produced a higher electric field strength at the insulator's end. Finally, the project recommends including a combined mechanical and electrical test in future evaluation. This test will involve applying specific values of mechanical and electrical loads simultaneously to ensure the insulator's resilience. So this is our group reference that we use to complete our project. And that's all from our group. Thank you.